Hello, hello. Uh, Welcome to all the students. I am Captain Rayla Sanju. Welcome to online classes from Department of Chemistry, Government Degree College, Peddapalli. The yesterday class, we completed some of the chemical reactions of carbonyl compounds, aldehydes and ketones. Today we are going to learn about the remaining chemical properties of the particular aldehydes and ketones. Here, uh, this hydrolysis process in this slide, please observe, ketones and aldehydes undergoes hydrolysis process will get this type of hydrates. Here, the position of equilibrium generally favors the carbonyl group rather the rather than hydrate. Generally, all the carbonyl compounds, aldehydes or ketones, generally favors the equilibrium process to carbonyl side rather than hydrate formation. But except in the case of very simple aldehydes such as formaldehyde, it undergoes hydrolysis process and gives hydrates because please observe in the structure of formaldehyde, here there is no electron donating groups. When we go to ketone side, acetone, it attached with the two methyl groups. These two methyl groups, the nature is electron without donating nature. Is it clear? Electron donating nature. Here there is no any type of electron donating groups. Is it clear? There is no alkyl group electron donating groups because that the formaldehyde less stabilized. Formaldehyde less stabilized. It undergoes reaction very fastly. On reaction with the water, it gives hydrate compound 99.9 percentage. It gives hydrate compound. Is it clear? Uh, in what way we'll discuss in the mechanism part. In the mechanism part we'll discuss. Here, here the reaction proceeds in base catalyzed hydration. In this base catalyzed hydration process, there is a two steps are there. The first step is nucleophilic attack and the second step is proton transfer step. What those steps involved in this reaction, please observe clearly. Here, in the first step, nucleophilic attack, the carbonyl group is attacked by hydroxide, here OH minus hydroxide, forming a tetrahedral intermediate. Forming a tetrahedral intermediate. Here please observe this hydroxy OH minus nucleophile. Here it is a strong nucleophile. This particular nucleophile attacking on carbonyl carbon. Here in between this carbon oxygen pi bond cleavage takes place. This oxygen gets negative and this carbonyl carbon attached with four different groups. In that case the structure is tetrahedral structure intermediate. That tetrahedral structure intermediate is unstable. That negative charge O minus negative charge immediately abstract hydrogen from water molecule. From water molecule in the second step. Here please observe. The tetrahedral intermediate is protonated. This particular tetrahedral intermediate is protonated by water to form the hydrate. This is the hydrate. Two hydroxy functional groups attached with a carbonyl carbon. This structure is named as hydrate. This is the second step, proton transfer step. Proton transfer step. In this proton transfer step, finally we are getting hydrate compound. This reaction proceeds in under base catalyzed hydration process. Base catalyzed hydration process, it involves a two steps reaction. When we go to another condition under acid catalyzed reaction, in this acid catalyzed reaction, when compared with the base catalyzed, it proceeds in three steps of reaction. In three steps. In the first stage, please observe, it is a proton transfer stage, and the second stage is nucleophilic attack, and the last third stage is another proton transfer stage. Okay. In these three stages, the reaction proceeds under acid catalyzed hydration process. Okay. Now, in this process, please observe clearly. Here, in the first step, please observe the carbonyl functional group is protonated, rendering it more electrophilic. Here, the electrons on oxygen electron shifted to hydrogen. This hydrogen abstracted from hydronium ion. Here we are using H3O plus hydronium ion. The complete reaction is proceeds equilibrium reaction, equilibrium stage. Under hydronium ion H3O plus proton transfer and to forms protonated carbonyl functional group. Protonated carbonyl functional group. Is it clear? Protonated compound. Protonated carbonyl functional group. This particular protonated carbonyl functional group on reaction with the nucleophile. Here we are using a water molecule. Water molecule. The protonated carbonyl function group is attacked by water. By water, forming a tetrahedral intermediate. Tetrahedral intermediate. This in this water molecule, the oxygen pair of electron that it acted as a nucleophile. This pair of electron bonds with the carbonyl carbon, and the first carbonyl oxygen positive charge neutralized with the pi bond electrons. We neutralized here, neutralized. Another side, this water molecule attacks on carbonyl carbon. Finally, um, here intermediate is tetrahedral structure intermediate. From this intermediate, abstract hydrogen, abstract hydrogen when we are using another mole of water molecule. Here it is also proton transfer step. The first step, proton transfer step, and the last step is also proton transfer step. From this proton transfer step, this particular proton from tetrahedral structure abstracted by water, here loss of again that what is that H3O plus hydronium ion removes from the this step, remove from the reaction. H3O plus, when we are using in the starting reaction H3O plus catalyst, that H3O plus again loses from the intermediate. Okay, this is the proton transfer step, and we'll get a final compound tetrahedral structure of hydrate compound. Hydrate compound from formaldehyde. From formaldehyde, we are getting this hydrate compound under acid catalyzed hydration process. It is a three steps mechanism in presence of acid catalyst, but in presence of base catalyst it is only two steps. It proceeds two-step mechanism. Is it clear? Is it clear, all of you? Okay, acid catalyzed is also completed. Now let us go to another hydrate formation reaction. Here, for most ketones, hydrate formation is unfavorable. Most of the ketones unfavorable hydrate formation, because the equilibrium favors the ketone rather than the hydrate. The equilibrium always favors the ketones rather than hydrate formation. But when we use only except formaldehyde and its derivatives, undergoes this hydrolysis process to give hydrate structure. Okay. However, the equilibrium for hydration of hexafluoroacetone, this is the structure, hexafluoroacetone favors formation of the hydrate. This is a very important compound. Please remember hexafluoroacetone. It is a very good example for hydrate formation reaction. From this compound on hydrolysis, it gives hydrate structure. It is the major product, 99.99% product will obtain from this hydrolysis process. Is it clear? Is it clear, all of you? Okay. This is about hydrate formation. Oh, this second part completed. Now, now let us go to another third part. Third part we'll discuss third part. Now another part. Just is a small break. In this part, first, these are all various types of nucleophiles. Nucleophiles. various types of nucleophiles: oxygen atom containing nucleophiles, sulfur nucleophiles, nitrogen nucleophiles, hydrogen atom containing nucleophiles, carbon nucleophiles. These are the various types of nucleophiles. We will discuss clearly once again. The oxygen atom containing nucleophiles, for example, H2O water molecule, H2O water molecule, ROH alcohol. This is the ROH alcohol, and hydrogen peroxide H2, O2 hydrogen peroxide. These are all oxygen atom containing nucleophiles. Next, sulfur nucleophiles. Sulfur nucleophiles, H2S gas, H2S gas, and this is the sulfur containing peroxide structure, thioperoxide. Here H2S2, S2 instead of oxygen. Here sulfur atom is there, sulfur atom attached to this chain. Next, nitrogen nucleophiles. Nitrogen nucleophile, the very good example is RNH2 primary amine. It is a primary amine. R2NH secondary amine. This compound is secondary amine. Next, these two are nitrogen containing nucleophiles. Next, we'll go to hydrogen atom containing nucleophiles. Hydrogen, AlH4 minus, aluminum tetrahydride ion. It is also one of the hydrogen nucleophile. Next, BH4 minus, BH4 minus boron tetrahydride ion. It is also one of the hydrogen nucleophile. Carbon nucleophile, just in the first slide reaction we discussed with use of carbon nucleophile. The carbon nucleophile, the very good example is RMGPR, RMGX it is called. The general formula is RMGX, Grignard reagent, alkyl magnesium halide, alkyl magnesium halide, Grignard reagent. Is it clear? From this Grignard reagent, R minus nucleophile generally attacks on that particular carbonyl function group. Here, cyanide ion. Cyanide ion is also carbon nucleophile. Triphosphonium here, triphenyl phosphonium ion. It is also one of the carbon nucleophile. These are all uh, new various types of nucleophiles. Nucleophiles. Is it clear, all of you? Okay, students. Uh, Now we'll go to hydrate formation, another um, reaction. Here, aldehydes are ketones containing this carbonyl function group, CO carbonyl function group. When aldehyde or ketone is treated with the water, here is treated with the water, the carbonyl group can be converted into hydrate. Is it clear? Can be converted into hydrate. Just now we discussed that tetrafluoro example, hexafluoroacetone compound. Just now we discussed again. Uh, Please observe again. This is the hexafluoroacetone. Hexafluoroacetone. It is suitable example for favors the formation of hydrate. Favors the formation of hydrate compound. Here, the most of ketones hydrate formation is unfavorable because the equilibrium favors the ketone rather than the hydrate. However, The equilibrium for hydration of hexafluoroacetone favors formation of the hydrate. Here, hexafluoroacetone on reaction with the water molecule to forms 99.99% this compound. Hydrate compound. Just now. Based on that hydrate formation reaction, the another example is acetal formation. Acetal formation. This reaction proceeds under acid catalyzed hydration process. Acid catalyzed hydration process. Here please observe. In acidic condition, an aldehyde or ketone will react with the 2 moles of alcohol to forms an acetal. This is the acetal structure. 2 moles of OR. 2 moles of OR function group attacks on this particular carbonyl carbon. 2 moles. It is just like a hydrate structure OR. Instead of OH, it is a OR. This particular carbonyl aldehyde, or it may be ketone, aldehyde or ketone, on reaction with 2 moles of ROH, 2 moles of ROH alcohol, 2 moles of alcohol in presence of acid, to forms here 2 moles of, we are using 2 moles of alcohol. From this, two OR function groups are available. 2 OR function groups attacks on this particular carbonyl carbon to give acetal. Acetal compound and byproduct is water molecule. Is it clear? Now we'll go to actual mechanism part of this particular acetal formation reaction. This acetal acid catalyzed hydration process, here we are using acid catalyst. Common acids used for this purpose include para-toluene sulfonic acid, here this one, general formula TSOH, para-toluene sulfonic acid we can use, or normal sulfuric acid, H2SO4, normal sulfuric acid we can also use as a catalyst in this reaction, acid formation reaction. Okay, and now we will go to actual mechanism part of this particular acetal formation reaction. Here, this is the actual mechanism. Please concentrate. Okay. Please concentrate actual mechanism part of this particular acetal formation reaction. Here, the carbonyl group, this is the carbonyl function group, is protonated, rendering it more electrophilic. These electrons are available on oxygen in this carbonyl function group. These electrons transfer to H plus. Okay. This is the acid we are using, a sulfuric acid, it's like, okay, HA acid. This carbonyl function group, in the first step, it converted into protonated carbonyl function group. Okay, protonated carbonyl function group. In this protonated structure, Here oxygen atom loses electron because immediately that oxygen atom gets positive charge. Here this is the protonated carbonyl functional group. Okay, this intermediate, the alcohol, the alcohol attacks the protonated carbonyl to generate an oxonium intermediate. This is the oxonium intermediate. Alcohol, this ROH alcohol attacks on that protonated carbonyl carbon on the carbonyl carbon. Immediately breakage of this particular pi bond and oxygen gets neutralized. Here oxygen gets neutralized. To forms another intermediate, it is a oxonium intermediate. Oxonium intermediate. This particular oxonium intermediate is deprotonated to form a hemiacetal. Deprotonation. Here extra proton is available on this oxonium ion. Extra proton. This proton abstracted by this A minus. Is it clear? Proton abstracted by A minus. The OH bond cleavages, immediately that oxygen O positive gets neutralized to converted as hemiacetal. Hemiacetal. Is it clear? From this hemiacetal, another step of proton transfer stage. The hydroxy group, this particular hydroxy group, the hydroxy group protonated with a acid protonated, thereby converting it into an excellent leaving group. It converted in this hydroxy functional group stage. It is not excellent leaving group. It is a normal functional group, hydroxy functional group. It converted as after transfer of proton from acid. After transfer of proton from acid, it converted as good leaving group. It converted as good leaving group. It can leave very easily as a water molecule. Okay. From this loss of leaving group, loss of water molecule. Here breakage of CO, loss of water molecule. Water molecule leaves to regenerate the carbon-carbon. After leaving of this water molecule, regenerates to the carbon-carbon, carbon-oxygen double bond. Here from our CO side, that OR function group in OR function group oxygen to forms another pi bond with the carbonyl carbon to forms a C double bond O. O. Okay, this structure. Next, nucleophilic attack. The second molecule, already first molecule ROH we used, 2 moles of ROH in this reaction generally we used. Please observe last step. Here this is the 2 moles. Okay, 2 moles on reaction with a carbonyl function group in presence of acid. Okay, here second mole of alcohol we are using. Second mole of alcohol. The second mole of alcohol molecule attacks the CO double bond to generate another oxonium intermediate. Here first oxonium intermediate is formed after attacking of first mole of ROH. Here also same. Here also same after that protonated carbonyl. Here alkylated carbonyl on reaction with another mole of alcohol to forms oxonium intermediate. To forms oxonium intermediate. From this another step, proton transfer step, that A minus ion abstract hydrogen from this oxonium intermediate. Okay, the oxonium intermediate is deprotonated, loss of proton here, deprotonated, and generating an acetal. This is the final acetal structure. In acetal, two OR function groups. Two OR function groups attached to the carbonyl carbon. This is the clear-cut mechanism of carbonyl compounds on reaction with the ROH, 2 moles of ROH in presence of acid to forms acetols. Acetols. Is it clear, all of you? Is there any doubt in this reaction? Okay. The similar reaction, another type of acetal formation, similar reaction. Similar reaction, acetal formation. Here, aldehydes are readily converted into acetols by treating with two equivalents of alcohol in acidic conditions. In acidic conditions. Here, please observe. Instead of ROH, here we are using ethanol, ETOH, 2 moles of ETOH, ethyl alcohol, acetaldehyde, here formaldehyde on reaction with ethanol, 2 moles of ethyl alcohol in presence of acid. Products are favored at equilibrium. In this reaction, because the starting compound is formaldehyde we are using, the reaction, equilibrium reaction favors product side. When we use here acetaldehyde, the reaction may be moves backward direction. The reaction, equilibrium reaction, in that case equilibrium reaction favors reactant side. Okay, but here we are using the starting compound is formaldehyde, because the formaldehyde compound aldehyde electron donating, there is no electron donating groups because the formaldehyde is less stabilized than acetone. Because it undergoes reactions very fastly, the equilibrium process favors two products. Okay, this product's formation. Clear? However, for most ketones, the equilibrium favors reactants. Here, reactants. rather than the products. Just now we discussed here acetone we are using instead of that last reaction formaldehyde. Instead of that formaldehyde here we are using acetone. In this acetone the major is two methyl groups. Methyl groups means plus I inductive effect groups, electron donating groups are attached to carbonyl carbon. In that case, this particular uh, ketone is more stable than aldehyde. Because this particular equilibrium reaction favors reactants side rather than products. But in the last reaction, in this reaction, the equilibrium favors product side. Products are favored at equilibrium. Okay, is it clear? Reactions are favored at equilibrium. Water molecule. Acetal acetals as protecting groups. This acetal formation is also used for protecting group. Here, acetal formation is a reversible process that can be controlled by carefully choosing reagents and conditions. It is generally that acetal formation reactions, all the acetal formation reactions are generally reversible reactions. In these reversible reactions, based on the reactant, it may that reversible reaction it may favors product side some of the reactions. In some of the reactions based on the reactants, the reversible process may favors product side. Product side. Okay. In that case, generally this type of protecting groups also used here. Um, this particular ketonic function group here we are using as a protecting group. This compound on reaction with the hydrogen peroxide in presence of acid. It it acted as a protecting group. In the reverse process again loses water molecule, it forms again carbonyl compound. This acetals as a protecting group, acetal formation is favors by removal of water. Here please observe that particular carbonyl compounds to acetal formation. Carbonyl compounds to acetal formation is favored by removal of water. To convert an acetal back into the corresponding aldehyde or ketone, it is simply treated with the water. Here please observe. In the first step, in the forward reaction, when we are using carbonyl compound on reaction with hydrogen peroxide in presence of acid, it it loses water molecule to forms acetal. In the backward reaction, the acetal is converted into carbonyl compound. In that case, in presence of water molecule, the acetal is converted into Again, carbonyl function group. It is simply treated with water in presence of an acid catalyst. The backward reaction, reverse reaction. Here, please observe reverse. This reverse reaction in presence of uh, on reaction with the water in presence of acid, that acetal compound is converted into the original carbonyl compound. Aldehyde, it may be ketone. It may be aldehyde or ketone. Is it clear? For example, consider how the following transformation might be accomplished. Here, carbonyl function group and ester function group present on that particular cyclic chain. How the reaction proceeds. In this reaction, um, carbonyl function group may be involved, changed, or ester group may be involved in the reaction. We'll discuss clearly in the in this reaction in this short time we cannot cover this particular reaction. For this reaction tomorrow we'll discuss acetals as protecting groups. Tomorrow we'll discuss clearly with the mechanism part. Okay, okay students. We'll meet tomorrow at the same time. Hmm? Thank you. Thank you, Anna.